Hi guys, I am here to give a presentation about my final year project Agrobot. So the people along with me in this project were Veday Shah, Neil Shukla, Nutan Sangani, all headed by HOD Dr. Kriti Srivastava. So what is Agrobot? Agrobot is an autonomous robot that will be able to identify a plant, give it the correct amount of pesticide based on its growth stage, and then cover the entire field autonomously without any human intervention. So what were the gaps? Once we went online and related to such a solution, we found the following gaps. The first one was that not all plants require the same amount of pesticides because some plants that are in early growth stages need a different amount of pesticide than ones in the later stages. So then the second one was not all farmers have Wi-Fi or good GPU or GPS coverage. Hence, we had to make a solution that did not include these factors but still could be able to navigate through the entire field. And we did so just based on one constraint that the field has to be one suggested by ISA research papers. So the ISA research paper says that the field has to be such that plants are arranged in rows and there is enough space between two rows so that a robot or autonomous drone can go through those. The third one was, as you can see, when we use a good enough model to predict a Spanish tomato, it predicts it with 97% confidence, but Indian tomato only with a 63% confidence. So we wanted to change this. So moving on to the problem definition. The problem definition was simple. It was to design and develop an automated pesticide spraying robot that can operate effectively on fields that have crops as suggested by the ISO research papers, and it should also be such that it can fit on a Raspberry Pi and is fast enough so that it could quickly navigate through the entire field, giving the correct amount of pesticides, not wasting the farmer's time. The objectives were four. That was making a dataset that includes indigenous plants and good enough images so that we could extract the geometries, textures, and different factors that we can identify and classify between a tomato plant and the rice plants. That is the scope of this project. Then the model development and accuracy was making a model with 85% plus accuracy. It should maneuver efficiently and should be good in testing and validation. So the data analysis, the main three datasets are tomato leaf dataset detection dataset available on Kaggle, rice leaf disease detection dataset available on UCLA, and the new plant disease dataset that contains more than 87,000 images of Indian plants. So the data analysis was, there were 16 total labels with 10 labels for tomato plants with diseases and 6 for rice plant diseases. The pre-processing was such that we did not want the model to just identify the leaf based on its background. So what we did was we made both the backgrounds same. Next one was removal of duplicate and correct images, and the trade tie split was 70-15-15. The data pre-processing also included standard dimensions like making, since a rice plant is big enough, we have to reduce it to such size so that there is concurrency between both rice and tomato images. So the model doesn't straight away classify it, because if an image is big, then it is rice, if small, then tomato. And then we normalize the pixel values. So let's move on to the model building. The hardware diagram consists of a Raspberry Pi that has power supply of 6 to 8 volts. They're followed by a camera unit and ultrasonic sensor. The camera unit is mounted on a servo motor so that the camera can move around and see. This is the basic vision setup. Then the spraying unit for spraying purposes and motor driver for moving purposes or navigation purposes. The YOLO model is a basic YOLO V8 structure. YOLO models are very good at detecting different types of objects in images. Then once an object has been detected, we have to identify whether it is a object. In this case would be a leaf, so we have to identify whether it is a tomato leaf or a rice leaf. So we applied different models, AlexNet models, VGG models, GoogleNet models. The best one that gave the least error was a ResNet model and had 152 layers, that was significantly higher than others. So this is a basic resonant model. These are convolution layers. These are residual layers that allow data to, you know, come forward so that less data is lost. And this was very helpful as it gave the highest amount of accuracy. Then to detect growth stage, what we did was we combined factors, mainly size and the greenness of a leaf. Since using both these factors, we can accurately detect or make a good estimate about the current growth stage of a plant. And this is the hardware circuit diagram, which consists of the Raspberry Pi and different pins that are connected to, let's say, the motor driver, the relay, or the ultrasonic sensor. The next one is the basic state navigation diagram. So the basic run through would be the robot would start, it would move forward. If it detects a plant, it would identify it and align with the plant and spray pesticide. Or if it did not detect a plant, it would continue moving. Once it even sprayed pesticide, it would continue moving. Now, once it continues to move, it would see if it is it end of row. If it is end of row, so it cannot see any plants in its 360 radius, then it would turn to the next row. If not, then it would continue moving forward and we would see the same cycle repeat. This is a basic UML use case diagram. The next one was the cost of components. It costed us total 7,000 rupees to make the entire robot. Then this is the test bed. The test bed consisted of a French field that had many different plants, each of height. Tomato plants were at a height of 25 to 50 centimeters. The soil was dry with some pebbles and an uneven terrain. There was also variety of plants other than tomatoes, so we could also check if our model was running good, or it could classify between tomato plants and other type of plants. So here are the results. So there were two main hypotheses. One was it should have at least 85% plus. The model should have 85% plus accuracy, which you can see when we use 128 layers, AlexNet, VGGNet, MobileNet, ResNet, all could do that. The next one was real-time processing capabilities. So along with accuracy, it should also be fast enough so that it could complete the entire spraying process within 60 seconds per plant, or if it could not. So what we found was ResNet and MobileNet could, while AlexNet and VGGNet were compact enough that they could not do it in less than 60 seconds. So what we did was we chose a trade-off, as MobileNet had less accuracy. So what we did was, let's take a model that is a little bit worse in terms of speed but good in accuracy. So this is our basic presentation. Now moving on to the video of it. So here's the demo, the official video. So this is the basic video of a plant. It moves forward, the camera sees the plant, then it moves away so that water isn't sprayed on it. Then it aligns with the pesticide, the spraying unit, and sprays on it. The next one, let's see the end of row condition. Since no plants are there ahead, it has detected that it will align with the plant and spray pesticide, and then it has detected that there are no plants ahead. So what it will do is, it will move forward, turn 90 degrees, then it will see, okay, I see a plant here and here. So it will go, it will move forward. It has already detected this plant. It will spray pesticide, move forward. See the plant, move the camera away and spray. So this is the basic demo of how the Agrobot works.